Hello, everyone. Welcome to this Wind Power Engineering and Development webinar, Site Assessment and Site Development, Getting the Most Out of a Wind Investment. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thank you for joining us. Now, I have to acknowledge our sponsors, which are Ultig and TWR Lighting. They manufacture the Orca safety lights for Met Towers and so on. Now, here's just a brief agenda before we really start. The webinar will be available at powerengineering.com. That's our website. And a link to it and the slides will be emailed to everyone. At the end of the presentation, we'll have a brief question and answer session. Now, of course, not everyone that wanted to watch today's webinar could do so, but you can help them learn from it by tweeting key points and the takeaway you think important. In your tweets, be sure to include the hashtag WindWebinar. After the presentation, I'll read the questions that you and the audience have submitted. You can do that by typing them into your questions box on the GoToMeeting panel that should be to the right of your screen. And you can do that at any time during your presentation, And I would suggest you do that when the questions come up. Don't wait to the very end to type them in, okay? And we'll answer as many as possible before the time is up. Now, let me tell you a little bit about our speakers, and then I'll turn the microphone over to them. Our first speaker is Michael Brower. He is the Chief Technical Officer of AWS TruePower, where he leads product development and helps ensure quality and standards across the company. He's a physicist and a prominent expert in the wind industry. He's led numerous assessments of utility-scale projects around the world. Michael's also known for his contributions to wind flow modeling and short-term wind forecasting. And our second presenter is Stephanie Van Kempen. She's a modeling specialist at AWS TruePower as well, where she provides expertise in wind resource mapping and validation, wind turbine layout and design optimizations, energy production estimates, and GIS analyses. She's proficient in the company software, which is wind farm design and spatial analysis, and is involved in the development and validation of company software, which is Open Wind Enterprise. Ms. Van Kempen provides technical training of Open Wind Enterprise to users, and she has recently co-authored an article on the software in our fine magazine. And with that, let's start with Michael Brower. Michael, the microphone is yours.
Thanks very much, Paul. I'm going to be talking today about really a wide range of topics, from site assessment at very early stage to some of the nitty-gritty details of designing a wind project. First, let me make sure I can get control here. Here's a quick outline of the talk. First, I'll just say a few words about my company so you know who we are and the kinds of things that we do. And then move on to an overview of the wind resource assessment process. This is really the most critical stage of developing a wind project. If you get the wind resource assessment wrong, then everything else regarding the energy production and the financial model will also be wrong. And so it's very important to get that right. And once I give a quick overview of that, we're going to move on to some of the details of the wind resource assessment process, specifically finding a developable wind site, also known as wind prospecting, tools for Met Tower monitoring and management, modeling the wind resource, that is the spatial distribution across a wind site, and finally other tools for effective wind development, namely the design software OpenWind. Next slide, please. AWS TruePower is a consulting firm that whose mission is to work with developers and investors to advance renewable energy worldwide. Renewable energy, in particular, solar and wind power. We provide a wide range of consulting and consulting services, as well as information products such as wind maps and data, which cover the life cycle of solar and wind projects, from the initial site identification and qualification right through due diligence, performance assessment, and then during the operational phase, real-time forecasting. Next slide. Oh, could you back up one? Okay, I've got it. Here's a company snapshot. We've done independent assessments of over 60,000 megawatts of wind and solar capacity around the world, working in over 80 countries. We've been around quite a long time, actually, since 1983, and have close to 30 years of industry experience. We have about 100 professional staff with expertise in meteorology, spatial analysis of the environment, and engineering. Um, we have main offices in Albany, Barcelona, and Bangalore, and I'm happy to say that we will be opening an office in Brazil, in the city of Curitiba, in this coming fall. Much of the material that I'm going to be discussing and that Stephanie will be discussing after me can be found with additional details and information on other topics in a book that was recently published by Wiley. It's called Wind Resource Assessment, A Practical Guide to Developing a Wind Project. And this was a collaborative effort by staff at True Power, and I was the editor of the book. This book covers the topics that you see there. And really the goal of the book is to establish the state of the art and provide guidance to people engaged in wind resource assessment, so that at the outcome of a wind assessment process, they can produce relatively accurate estimates of the energy production of a wind project. So I recommend that those of you who are interested in going beyond what we present here in this webinar, that you can get this book through either through Wiley or through Amazon.com. This is a overview of the main elements of the wind resource assessment process. You can see at the left, the first step is site prospecting, which is the process of surveying a region, which could be quite large as a country, or could be really small, in order to find the best, most attractive sites for wind turbines. Once a site or several sites have been identified, then the next step is usually to conduct a wind monitoring campaign, which can last 1 to several years. And it's during this campaign the wind is measured with high accuracy, and those data that are collected then become basis for the rest of the analysis that occurs. After the wind had been collected, there's a data analysis phase, and then very often preliminary reports are produced through the course of the measurement campaign. And finally, once enough data has been gathered, there's typically a wind resource modeling stage where a numerical wind flow model of some kind is run in order to estimate the wind resource at points where measurements haven't been taken at the site. And finally, all of these data will go into an energy production report, which in most projects forms the basis for financing a wind project through banks and equity investors. And as you see, if you do this process right, then you can wind up with a successful project like the one you see in the photograph there. Now I'm going to focus a little bit on site prospecting, because this is one of the key phases, and it's typically for people who are new to the wind industry, it's often the first thing that they engage in is to find a good site in the area that they're interested in. This is a list of some of the key considerations that go into selecting a site. Of course, the first of these is almost always the wind resource. The wind resource is measured a number of different ways, but it's very common to hear people refer to a site by its annual average wind speed, which is usually expressed in meters per second. And that is usually at the height of the wind turbine that is likely to be used, which is these days probably 80 to 100 meters above the ground. So typical sites in the US, and especially that are being developed these days, have a mean wind speed at hub height of at least 6 meters per second, and very often more than 7 meters per second. Now, of course, before you have measurements, you don't have any direct indication, usually, of the wind resource at a site. This has to be estimated, and I'll be talking a little bit about sources of data that you can use for this. But generally, people will use wind maps, which are available from a number of sources, stations, and as well as other information, vegetation, such as the deformation of trees from the wind is another sort of kind of indicator that can be used as a clue, but of course it doesn't provide a very accurate indication. Now, aside from the wind resource, another important factor for utility scale projects is access to transmission lines, and typically sites have to be fairly near a transmission line at least 115 kilovolts or kV. That's usually adequate if the transmission line has enough capacity on it. That's usually adequate to support a project of 100 megawatts or more. A typical distance is usually less than 20 kilometers. And the reason why it's difficult to develop projects that are much farther from transmission lines is both the cost of building a transmission line to connect to the grid, and also the risks associated with that, because very often it can be you have to go through an extended permitting process, and that can take time as well as arouse opposition to the project. So it's an important consideration. Other factors to consider include the constructability of the site. Sites with moderate slopes and good road access are important. Compatible land uses are another consideration. In this regard, rangeland and grassland as well as private farmland are generally preferred. And then so on. You can see some of the other factors there. Many of these issues can be quantified and brought into a geographical information system, or GIS, and that is an essential tool for planning most wind projects these days. On this slide, showing one example of an online tool for looking for prospective wind project sites. This tool is called Wind Navigator, and you can see the web address there. It's an AWS TruePower tool. And with this, you can access directly high-resolution wind resource maps, which are good enough in most parts of the world to get a very reasonable initial indication of the wind resource at a site, as well as the potential energy production for different turbine models. You can see that with this tool, you can get information such as the direction distribution of the wind. In this case, the wind is mostly from the northwest, as well as the seasonal distribution and other data that you can get through reports and other products that are available through the site. So this type of tool is now quite widely available and is very effective for the processing process. This is the result of a further site selection that can be done. This is usually done by a consultant. Here you see that two sites have been selected, which are outside of the park areas or national forests that are indicated by the hatches marks, and are also relatively close to the transmission line that you can see running in the lower left-hand corner. The background here is a wind resource map. So you can get quite precise outlines of potential wind project area this way. Once you've selected a site, then you move on to the monitoring campaign, and this is a very important stage of the process, because this is where you collect the data that really forms the foundation for your entire resource assessment. Most monitoring campaigns these days rely on tall towers, at least 60 meters high. Some towers may be 80 meters or even taller. Remote sensing, SODAR and LIDAR in particular, are growing in popularity. These are instruments that can be set on the ground and can measure the wind up to heights of 150 meters or more using sound or laser beams. But these aren't primary instruments in most cases. The typical tower will have two cup type anemometers on each of 3 heights. An anemometer measures the wind speed. You can see a picture there on the right. The tower will generally have 2 direction vanes, pictured there on the lower right, and then a temperature sensor and maybe some additional optional instruments such as pressure sensors and vertical wind speed sensors. The number of towers depends on the size of the project area, and but the main guideline that we like to emphasize is that towers should not be placed in the best locations, but rather in locations that are representative of where turbines are going to be placed. That's the best way to obtain an accurate estimate of the wind resource that the wind turbines are actually going to see. And finally, at least 1 year of data collection is strongly recommended to avoid problems or biases caused by seasonal variations in the wind. Here's a picture of a 50 or 60 meter tower that's being installed. This is a tilt-up tower. So the instrument are typically attached while the tower is lying flat on the ground. And then using a winch and pulley system, the tower is raised to a vertical, and it's stabilized using guy wires that you can see attached to the tower here. And that's another view of the tower when it's almost vertical. Once the tower is installed, then the data need to be collected, and this can be done using a variety of tools and software. There are online data management tools available as well, such as this one that you see here. In this case, the data are transmitted automatically to a central server, and are then go through a quality control procedure. And once that's completed, they become available to be viewed by the customer or the developer. And you can see summary information about that site, including wind speed data, wind roses, and as you can see here, pictured here, this gives you an indication as the resource campaign is moving ahead of how well the site is doing. And here you see a blow up of some of the information that you can get. Whoops. After the data have been collected and quality controlled, then typically there's some preliminary wind resource reports, but those apply only to the locations where the wind has actually been measured. In order to get an idea of how the wind varies across your site at the locations where turbines might actually be installed, it's usual to use a numerical wind flow model. And this allows you a number of things. First, it allows you to optimize your plant layout. You can place your turbines where they will be the most productive, produce the most energy. And also, once you've settled on a layout, it becomes the basis for estimating how much energy those turbines are going to produce. And so it's a very important component of your final energy production estimate. Wind flow modeling is also one of the largest sources of uncertainty in wind resource assessment. You can see here, these are some of the factors that contribute to uncertainty in a typical resource assessment. And of these, wind flow modeling is often by far the largest source of uncertainty. For that reason, we recommend using a significant number of towers at a site in order to measure the wind resource in as many points as possible, and also using a very high quality wind model, which, for example, a model based on a numerical weather prediction software like we run in our SiteWind system. This is a typical output from a wind flow modeling exercise, and you can see here what you have is a high resolution wind resource map in the background. And on this map have been overlaid the locations of the turbines that have been optimized using plant design software. And from this process, you also get additional information that can be used to actually estimate the energy production. Now, at this stage, we move into talking about plant design and optimization software. And we're going to be introducing you to the OpenWind software, which is AWS TruePower's software. This software has is one of the newest to be developed. It's exceptionally flexible, designed for a wide range of use. It's compatible with all the leading file formats and is based on a GIS architecture, which means it's very compatible with geographical information systems that are used in other aspects of the project design and development. There's an open source version of this, and there's also the OpenWind Enterprise, which is the commercial version that has additional capabilities. With that, I'm going to turn the microphone over to Stephanie, who's going to talk to you in more detail about some of the capabilities of OpenWind and how it's used in actually designing and assessing a wind project.
Thank you, Michael. First, we'll just start with some of the features that OpenWind has to help you with your site assessment process. Michael was discussing earlier about wind flow models. There is a wind flow model within OpenWind. It's a mass-consistent model and does fairly well in both simple and moderate terrain. The inputs required for this model are met mass data, scale to hub height, elevation data, and roughness data. Now, it's recommended that you extrapolate the measurement data up to hub height prior to importing the data into OpenWind. The wind model can use the shear map to extrapolate to hub height. However, this is generally not a good idea with any wind flow model. Now, while the wind flow model within OpenWind does provide a good depiction of the wind across your site, like Michael stated earlier, it's recommended to use a more advanced model for your final wind flow assessment. An example of this being the AWS Site Wind System. OpenWind the OpenWind Uncertainty module is actually designed to work with the Site Wind System as well as wind resource grids from other wind flows such as the CFD, etc. Can also be used. Now, wind flow assessment at your site is not the only important factor. Another key piece is the turbine layout design. Now, there are several key items you should consider while designing a turbine layout for your site. Completing turbine model selection based on site-specific climatic conditions is important to ensure that the turbine used at your site will maintain an appropriate turbine loading as identified by IEC standards. Each turbine model is designed to withstand different site conditions, such as wind speed and turbulence levels. Additionally, turbines must meet the manufacturer's suitability analysis to get a warranty. So by doing a climatological-based turbine selection up front, you're more likely to get a warranty from the manufacturer. Choosing the most appropriate turbine model will help you to maximize your energy production while limiting major systematic breakdowns and maintaining the lifespan of the turbine. Placing turbines along features and on the windiest areas of the site is also an important aspect. You can see in this picture on the right here that the turbines are clustered along the windier area, kind of these ridgeline features here. This will help to maximize your energy production, but while doing so, you should also consider wake effects and turbine loading from each of the turbines onto each other. So it's important to choose an appropriate minimum downwind and crosswind spacing based on your turbine model and the site conditions so that the wake losses will be at a reasonable level and won't lead to unnecessary fatigue in your turbines. You can see here that each of these turbines is separated by a minimum spacing here, and that'll just help to reduce your wake losses. Finally, constructability is an important aspect to consider. It's generally a good idea to design a layout which is relatively compact and does not have turbines that are so far away that that stringing, cabling, and road networks out to them will actually be more expensive than the energy return that you'll get from that turbine. This is typically a fine line to walk along, and within OpenWind there's a tool called the Cost of Energy Optimizer, which will help to limit the road and cable runs and utilize current infrastructure to help design that cost-efficient layout. So the Cost of Energy Optimizer differs from a standard energy optimizer in that it works to minimize the cost of energy and not just maximize production. The optimizer works to create a layout which balances energy production along with construction costs. Within the optimizer, there's a simple financial model, and you can input basic financial assumptions such as the total life of the wind farm in years and the debt interest rate. And there are also options for setting up costs associated with roads and cabling, which we'll get into in a little bit. Using all of these inputs, the Cost of Energy Optimizer will work to find the optimal plant size. You can start the optimizer with a set number of turbines and choose an option to have it only add turbines to the site if the incremental cost of energy is falling. So therefore, you'll get you'll get the correct number of turbines for your site as an optimal plant size. So then while the optimizer is optimizing, it'll identify and eliminate high cost or stranded turbines. So it'll move them closer to the bulk of the array, which will help to create a more compact and lower cost layout. Now I have a quick video here to show you the optimizer in action. Heather, so you can see here the optimizer in action. You can see that the turbines are clustered closely together and in some main features throughout the site, and there's really no stranded turbines in that middle area or off to the edges at all. And you can see here that the cost of energy is about $24 per megawatt hour. So when you're optimizing, it'll actually assess the cost per turbine and give you an estimate average for the site, so you can see how your costs are doing as the optimizer progresses. So another feature of Cost of Energy Optimizer is the design and cost of road and cabling networks. These are a large portion of the infrastructure costs that go into the construction of wind farms. And for each iteration of the optimization, OpenWind will actually develop a reasonable road and cable network, and this will provide the basis for the per turbine costs as the optimizer progresses. To most accurately design the layout and calculate turbine costs, the user has the capability to define parameters and costs associated with these networks. So for example, for the road network, you can define costs associated with cost per kilometer of the road and what cost savings you might have if you were to use existing roads, the maximum gradient of roads, and other factors. And you can also define different parameters for your collector system as well. And you can set the substation location up here, or the cost of cross water bodies, and some different cabling type information. And now OpenWind will automatically divide the layout into circuits and provide cable type information for the final cabling network used in the optimization. So if you were to run a cost of energy report, which you can do for any layout, whether or not you've optimized it within OpenWind or not, you can run a cost of energy report, which will give you metrics on a per turbine or a per site basis for the cost of those turbines. And you can actually see which turbines might be higher in cost compared to the rest of the layout, and make decisions on whether or not you want to maintain those within your layout or not. Another feature within OpenWind is the deep array wake model. Wake losses are an important aspect to consider within your turbine layout design. Now, standard wake models assume turbines do not modify the ambient flow, and that it's a one-way process, really. but evidence suggests that large arrays can actually reduce the available energy in the boundary layer, and that it's really a two-way process. So this has been verified through research by AWS TruePower using both onshore and offshore wind projects. And you can see in this image here an offshore wind project, and you can actually see the wakes coming off of the backs of the turbines extending throughout the further back rows in the array. Now the deep array wake model is based on a theory by Sten Franzen, in which an infinite array of wind turbines is represented as a region of uniform high surface roughness. And this roughness can actually impose drag on the atmosphere and cause changes in the boundary layer and reduction in the free stream wind speed. So within the deep array wake model, this theory has been taken a step further to determine wake specs on individual turbines. And it's used in combination with a standard wake model, such as Ainsley's eddy viscosity wake model, for example, to accurately predict the wakes in both shallow and deep wake zones within the layout. So when the deep array wake model is enabled, it will estimate the wakes at the site without the need for the user to specify whether or not they believe the layout is a large array. So this will allow users who are not experienced in aerodynamics to still accurately predict the wake losses at their site, because OpenWind will determine which of the two, whether or not the deep array wake model modifier or your standard wake model is the appropriate model to use on a per turbine and per direction sector basis, actually. So using the deep array wake model during the optimization process will help in aid in your turbine layout design and help to reduce wake losses throughout your site. Another useful tool within OpenWind, which can help to maximize your energy production, is the time series energy capture tool. This models the plant output from moment to moment rather than using standard frequency tables. The standard frequency tables only use the aspects of wind speed and direction and do not use the time element to do the energy capture. So the time series energy capture gives the user the ability to model effects of seasonal and diurnal variations seen in the observed data on factors such as wake losses, turbulence intensity, air density, temperature. You can calculate a high temperature shutdown loss, for example. You can produce time series of net energy over any period that you have observed data for, and there's customizable reporting of values per turbine and or per site. And since you're really downloading the data or importing the data directly into OpenWind, it will bin the turbulence intensity tables for you, and you also have the ability to rebin your data into a different number of direction sectors right there within the software. So you can see here in this picture on the right that this data has actually been binned into 36 direction sectors instead of 12, for example. So you can do that right within it and see when yours is at different number of direction sectors right there. Now, turbine scheduling is a tool which utilizes the time series energy capture, and it's got multiple uses, primarily for assessing the effects of environmental curtailments, such as bird migrations or bat curtailments, for example, or it can be used to calculate the energy loss due to noise curtailment, or if turbines need to be turned off during specific times. So if you've got, say, a bat curtailment, for example, you can actually set it up within OpenWind and specify the times of day and the times during the year which the bat curtailment needs to be applied, and calculate a loss due to that curtailment. So having the time series data within OpenWind allows for these time-based losses to be calculated and gives a better estimate of what the losses will be in real time, while considering other factors such as your wake losses on a time series basis or your air density changes on a time series basis. So in conclusion, using state-of-the-art methods and software, energy production estimates can be highly accurate. Each of the steps along the way, from wind resource to wind flow modeling to turbine layout design, contribute to the outcome of the wind farm and its return on investment. OpenWind provides advanced tools for minimizing cost of energy and designing the best layout for your site. And additionally, AWS TruePower's online tools, such as the data management tools that Michael mentioned earlier, and our staff experts can support project development. I'll turn things back over to Paul now.
Okay, great presentations, Michael and Stephanie, and I feel smarter, and I think the audience wants to get smarter too because they've been typing in questions very busily. So let's start with this question, Michael. This one's for you. A viewer asks, how far can you go into a site assessment without having on-site wind monitoring data?
That's a very good question. It depends on the site, the size of the project that you're considering, as well as the quality of the data that you have available to you. For example, some very small wind projects may be developed without on-site monitoring at all, but that's quite unusual. Normally, what the online data would do is help you to choose a site and bring it to the point where you think that it might offer a good prospect, and it allows you to estimate the energy production in an approximate way. But in order to go any further, in order to make any serious investments in the site development, you really need to monitor and set up instrumented towers. Mm-hmm. So it allows a preliminary site identification and ranking, and some preliminary estimates that can be used in your financial planning, your financial models. But before you spend much more money, you really need to measure.
Mm-hmm. Okay, very good. Okay, hey, this question for you, Stephanie. Can OpenWind Enterprise use the output of other wind flow models, such as WASP or WindSim, in extracting time series events and so on?
Yes, OpenWind is compatible with a variety of file formats, and you can import a wind resource grid, any of the model outputs from the other models there, bring it right into OpenWind. You just need your meteorological data to be on a time series basis to use the time series energy capture tool.
Okay, very good. Another reader or viewer asks, what considerations should we have when we have woodlands? Michael, why don't you give that one a shot? The viewer's asking about woodlands on a potential site. What kind of considerations would you give that?
Well, that's a good question. I'm not sure whether the concern is about whether it would be acceptable to build a project in woodland area. A serious impediment. It does have to be taken into account in the resource assessment, especially in the wind monitoring and the wind flow modeling phases, since tall stands of trees will affect the wind resource that's seen by turbines. You also have to think about how much the presence of woodlands or woodlots will affect the cost of construction, since the trees will, of course, have to be cleared both in the monitoring phase and when building and installing the wind turbines and the roads and cabling and so forth. So having woodlots on a site, generally, if they're in areas where you'd like to put wind turbines, it will generally increase your costs. But otherwise, it shouldn't pose an insurmountable problem.
Okay. Can taller towers accommodate some of that forest?
Yeah, certainly. And in fact, towers and turbines are now so tall that trees have much less of an influence than they used to in the early days of wind project development. So the direct influence of trees on the wind resource is generally pretty small, probably no more than 2 or 3% on the whole. Of course, you still have to clear the trees to install the wind monitoring towers and the turbines and roads eventually when the project gets built.
I see. Very good. Okay. Here's a question for either one of you. Please discuss the use of LiDAR. And maybe include in that response maybe the use of SODAR as well.
Sure, I can take that one. Well, LIDAR is becoming increasingly popular in wind resource assessment, both LIDAR and SODAR, especially these days LIDAR, because it's generally regarded as being somewhat more reliable and accurate than SODAR, although that's not always the case. It is, however, much more expensive than either SODAR or a conventional METMAST. So it's really in a transitional stage right now where LIDAR is used as a supplement in wind resource monitoring campaigns quite often, especially to look at difficult or complex situations where it's suspected that the wind shear might change with height above the height of a wind monitoring mast. It can also be used as a spot check of the wind resource. Since these are mobile units, you can move the LIDAR around and monitor several locations over the course of a year, as opposed to setting up a permanent mast which stays in one place. So it's becoming increasingly important, and possibly in the next few years will become the mainstay of wind resource assessment campaigns.
Okay, very good. Another viewer asks another question, but his question really is there a potential to reduce the prospecting time or provide a more complete data set with LIDAR?
I don't think that the prospecting time can be significantly reduced with LIDAR because you still really need to measure the wind for at least a year, and that's usually done with a permanent METMAST because that it's fairly low cost once it's installed, and it will remain in place for several years, and you don't need to worry about it. So really, a LIDAR is used to supplement the information that's available from the permanent MET towers by refining understanding of the vertical wind profile and also just providing more measurements around the site.
Okay, very good. We're going to keep you busy, Michael, here. Another reader asks, or viewer asks, are we looking at about a 5 to 7 year process from site prospecting to the energy production report? He's asking about the length of time from
that's probably
project.
Yes.
Go ahead.
Yeah, for larger wind projects, I think that's probably not a bad estimate.
Oh.
It takes several months to identify a site, and then you have to get the permits for wind monitoring if those are required. Then you have to secure the agreements with the landowners, set up the tower, wait a year or maybe even 2 years to get a good amount of data. Then you go into the process of designing the project and securing financing and so forth. So 5 years maybe is a bit long, but we've certainly known projects that take that long. I would say that it's at least a 2 year process.
Okay, thank you. Stephanie, why don't you try this one? The listener asks, is the free USGS NED data good enough for a site assessment?
Oh, yes, absolutely. For most areas of the United States, I think they actually have 10-meter data available. But for all of the United States, there's 30-meter data available, and you can bring that right into OpenWind, and that'll, on a per turbine basis, the elevation estimate will be used to figure out a per turbine air density, which will be input into the energy production estimate and the energy capture routine within OpenWind. But yeah, the USGS data is that's a high enough resolution that I would recommend using that for sure.
Okay, great. All right, Michael, I think this comes back to you. Can you break down the approximate time for each component, site prospecting, monitoring campaign, data analysis, and so on?
Well, I can try. You know, the site prospecting phase itself can take a couple of years if you're starting from scratch and you're looking at a very large area, or there are a number of sites that you might want to consider. More typically, you might say six months to 12 months to identify and secure a site for a small to medium-sized wind project. Then you're probably looking at a year to 3 years for the wind monitoring. How long you monitor depends in part on, well, the longer you monitor, the lower the uncertainty of your estimate will be. And that will help your project financing and allow you to hopefully to secure a better deal and leave less money on the table. So it's generally a good idea to monitor longer, but that increases the cost and it's a delay. So there's no maximum time period, but typical time periods is between 1 and 3 years for the wind monitoring. Then you can go into quite an extended phase of, it's not so much the design process, because the process that Stephanie outlined doesn't have to take very long. But there is for example, negotiation with a wind turbine supplier, discussions around permitting. If there are issues concerning, say, wildlife that concerns have been raised, then that can be a further delay. If you're building a transmission line, the longer that line is, the more time it usually takes to secure the necessary permits. You may have to go to a state level process as opposed to, say, a local process. So there are lots of issues that can come up. So that phase could take anywhere from 1 to 2 years as well, and so that could bring you out to 5 years in all. Once all of that is in place, then the process of actually building the project may only be a few months. It doesn't take that long once everything is in place, but the planning and all of the preparatory work can certainly take a good amount of time.
Oh, goodness, all right, thank you. Hey, Stephanie, try this one. Do you have comparisons of projects where you provided estimates and compared those with actual values, actual wind resources after the fact? See the viewers asking?
Sure. AWS True Power's methods have been verified with operational data at. We just did a study recently that had 46 wind farms, I believe, with over 100 years of operational data. Our AWS True Power's methods have been verified against that data. And in addition to that, the deep array wake model that I was discussing, which is within OpenWind, as part of AWS True Power's methods as well. But the deep array wake model has been independently validated with operational data from both on-site or onshore and offshore projects. There's on the OpenWind website, you can actually go ahead and download the deep array wake model validation paper if you're interested in a further discussion on that.
Okay, very good. All right, Michael, maybe this one's for you. We're going to go off country now. South Africa has some of the highest lightning incidences in the world. What considerations would be relevant in this regard, considering effects related to height?
That's an interesting question. Well, lightning can come into play at various points in the project development. In the wind resource assessment phase, you need to worry about the survival of your monitoring equipment, and in areas that are prone to lightning, it's very recommended to have extra lightning rods and extra heavy gauge cabling to redirect lightning away from the instruments, and some other protective measures as well. So it's an important factor to consider even at that stage. In the actual operation of a wind project, lightning generally doesn't pose much of a problem, but it can cause outages of both individual turbines and, say, substations and other equipment. So lightning is a factor in determining or in estimating the losses that are likely to occur from wind turbine downtime. It's usually not a big factor. It's not one of the first concerns. Really, where lightning is most important to consider is in the wind resource assessment phase, when you really don't want to lose your equipment and have a lot of outages, and as well as need to replace your equipment. So.
Okay, good. Thank you. Michael, you're going to be a busy boy here. What's the approximate cost of increasing from a 60-meter Met tower to an 80-meter Met tower? And does this increase usually justify the decrease in uncertainty of the data, assuming the wind turbines will be at an 80-meter height?
That's another very good question. Well, it used to be that there was a big transition in cost from 60 to 80 meters because that was where there was a transition from a tilt-up towers that were available at the time to lattice-type towers that were constructed in place and were usually typically more expensive. That's changing. There are now 80-meter tilt-up towers. So I think the cost penalty has gone down, but I couldn't put a number to it. The Generally speaking, well, there's something of a race between the heights of wind turbines these days and the heights of towers used in resource assessment. In the early days, turbines were maybe 30 meters tall or 20 meters tall in some cases, and towers were 10 or 20 meters tall. Now turbines are reaching 100 meters in height, and towers are typically 60 meters or 80 meters height. So there's always a bit of a lag there. Generally speaking, though, the wind shear, or that extrapolation from the top of the tower to the hub height, is not the largest source of uncertainty in energy production estimates. Usually there are other factors that are more important, such as your long-term climate reference or your wind flow modeling. So although there are certainly exceptions to this, as a general rule, having, let's say, one 80-meter tower or a LiDAR campaign or a SODAR campaign and a number of 60-meter towers is usually adequate for getting a reasonable uncertainty on your energy production.
Okay, good. Very good. Stephanie, your turn. This is a long question, so bear with me. Okay. Have there been studies done to correlate the Wind Navigator 2-kilometer data from data from an actual measurement campaign to come up with an average uncertainty value? In other words, he asks, a quantitative reason to run a wind measurement campaign as opposed to using just using your online site assessment tool values. Do you want me to read that again?
No, I think I got it.
Go ahead.
I'm not sure if I can pinpoint an actual uncertainty number based on the 2-kilometer data, but I mean, it's definitely recommended to put up your own meteorological towers and collect data at your site. I mean, typically we do, when we do wind resource, when we do our wind flow models, we do it at a 50-meter resolution for financing purposes. When we do our energy production reports, we do 50-meter resolution, whereas that 2-kilometer data is obviously a lot lower resolution. I mean, I think it's more recommended that it's just used as a reference and not really for coming up with any final energy production estimates. I'm not sure if Michael, if you know the exact uncertainty estimates associated with those maps online.
Okay, thank you.
Sure. Well, it depends on the region, but the 2-kilometer resolution maps typically are about 2 to 3 times larger errors. The higher resolution maps, the 200-meter maps. And in the U.S., that would be on the order of, say, up to a meter per second in uncertainty, as opposed to, say, a third of a meter per second for the high-resolution maps.
Okay. And here's our last question. Maybe, Stephanie, this is for you. What are the reasons for or against a power curve performance test?
Maybe this one's for Michael.
Okay.
Sure. I can take that. That's actually a interesting question, and one that different people will disagree on. Power curve tests are ultimately they're used to keep the turbine manufacturers honest. If you build a wind project and you want to make sure that the turbine is performing to their specification, and so it's quite common to test 1 or 2 of the turbines under very controlled conditions. And if the turbine fails that test, then the turbine manufacturer is required to provide some kind of to rectify the problem in some way. As a practical matter, unfortunately, power curve tests are designed in such a way that it's very, very rare for turbines to fail. What happens is, well, in a typical contract, the turbine is required to meet a certain threshold minus the uncertainty of the test. And that uncertainty of the test is defined quite broadly, which means that almost all turbines will satisfy the test. And so it's not really holding the manufacturers accountable as much as they should. This is something that's kind of an ongoing argument between manufacturers and project developers. So the actual value is probably less than it should be, and nevertheless, it is still, for most wind projects, a requirement that at least one of the turbines be tested.
Okay, very good. All right, I want to thank Stephanie, Michael, and want to thank the audience as well. We're running out of time, ladies and gentlemen, so once again, this webcast will be archived and available for reviewing at windpowerengineering.com. Just one final message here. You can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their time and attention. And from the staff here at Wind Power Engineering and AWS True Power, we wish you a good and productive day.